Welcome, Chem 252 Lab. This week's, or I should say, today's lab assignment is really going to be a Carbon NMR worksheet, similar to last semester where we worked through a Proton NMR worksheet. Carbon NMR is going to look at unique carbon environments, and depending on symmetry, every single carbon, if it has a unique environment, will usually show up as its own peak on a Carbon NMR. What's on the screen now is just a basic guide of the different regions where certain carbon environments will have a peak show up, where things like methyl carbons will show up early on in the lower parts per million, and things like carbons that are participating in a carbonyl environment will show up in the higher ppms around 160 and above. And this is just a basic guide and typically is usually pretty accurate. Just to actually get into interpreting Carbon NMR, well, when it came to Proton NMR, there was a lot of coupling that was observed, where essentially you would see some proton environments that would exist as maybe couplets, triplets, multiplets, singlets. And in Carbon NMR, if we were to still allow each region, each carbon environment to exist as couples or coupling, it would cause a huge mess across the spectra. So what's actually done is, for Carbon NMR, broadband decoupling is used, where essentially the entire carbon environment, instead of showing up as a triplet or multiplet or a doublet, they will only ever show up as singlets. Therefore, each peak that shows up on a Carbon NMR will be to one unique carbon environment, and you're not going to look for coupling of any kind. You're just going to look at each individual peak on a Carbon NMR, and that will represent one unique carbon environment. And if there's symmetry, then that in the molecule, then that peak might represent two different carbons or more, but any peak that you see on a Carbon NMR typically represents just one unique carbon environment. And let's go about how we can interpret the Carbon NMR that we're looking at right now to identify which molecules are represented in these spectra. Well, the blank NMR on the left, what we can notice is that the peak with the highest ppm, that ends at around 70, 75. Therefore, there's no peak with a parts per million above 80. And what that basically tells us is, if we go back to our spectra, anything that's above 80 would typically be a triple bonded carbon-carbon triple bond like in alkynes, or a nitrile group, a C triple bond N, aromatic carbons, or a carbonyl, C double bond O. So we have no carbon environment in the left spectra that has any of those groups. So automatically we know we don't have our rightmost molecule, which is a nitrile, which has nitrile groups, nor do we have our middle molecule or a molecule on the left, because both have aromatic carbons as part of a benzene ring, and the one on the left also has a carbonyl carbon, or specifically two, but none of those carbon environments are on the spectra. Therefore, we know we're either looking at this alcohol right here or this ether group right here. Now, one thing we can do is count up the individual peaks and to see how many unique carbon environments we have. For the left spectra, we have 1, 2, 3, 4, and 5 peaks. And if we just go by that, we can count the number of environments, carbon environments, in our remaining two molecules. Well, as far as carbon goes, we have the carbon attached to a single alcohol, and then we have one more carbon, and then based off of symmetry, the methyl carbons would show up as one unique carbon environment. So the alcohol actually only has 3 unique carbon environments, but our spectra shows 5. If we go to the ether, just going from left to right, there is no symmetry, therefore each carbon is going to be unique. We have 1, 2, 3, 4, 5. The ether molecule has 5 unique carbons, so based off of that, we already know that we're looking at the ether molecule for our left spectra. But we could also go one step further. While we have nothing above the 80 part per million region, or the 80 ppm region, which is what allowed us to cancel out anything that had a carbonyl, aromatic ring, or a nitrile group, both of these molecules, the alcohol and the ether, they have carbon single bonded to oxygen. And if we look at our peak table, a carbon-oxygen single bond typically shows up around 60 to 80 parts per million. Now, if we look at the 60-80 parts per million region on our spectra, what we actually see is that there are 2 peaks, or 2 unique carbon environments that are likely due to a carbon-oxygen single bond. So we're looking for a molecule with 2 unique carbon-oxygen environments. Well, if we go to our alcohol, we only have 1 carbon-oxygen environment, and it would be for this specific carbon right here that has a single bond to the alcohol oxygen. Therefore, that would not be the molecule because that would only show up as 1 carbon environment in that region. But here, what we have is actually 2 carbons that are single bonded to an oxygen. And since this molecule is not symmetric, those 2 carbons would show up as unique carbon environments or have unique carbon peaks in the carbon-oxygen single bond region. Therefore, we have 2 carbon-oxygen single bond peaks. Only the ether molecule has that going on. We also have essentially 5 unique carbon environments, which also tells us we're looking at this specific molecule. And since we have no peaks beyond the 80 part per million region, that's how we were able to cross out the aromatic rings, the carbonyl carbons, and the nitrile carbons. So any bit of information would eventually lead us to the left spectra being for this ether molecule. Now for our right spectra, essentially we have multiple avenues to decide. One thing we can look at is that we have, for this right spectra, we have 1 alkyl region. We have multiple aromatic peaks, specifically 4, and very uniquely we have a peak in the aldehyde ketone or carbonyl region. Well, just going by this peak that's between 160 and 170 parts per million, our guide tells us that that is for a carbon double bond oxygen environment. So a carbon that has a double bond oxygen. That would only show up due to this molecule all the way on the left. Everything else is either something with an oxygen, with an alcohol, no carbonyl, an ether, and again no carbonyl. Only the molecule all the way on the left has a carbonyl group. Now, some additional information we can use. We only have 1 unique alkyl environment, and what I mean by that is if we're looking at just typical carbons with 1, 2, or 3 hydrogen, they show up early on in the ppms, parts per million. We only have one unique alkyl environment, so something that's not aromatic, not a unique carbon like a carbonyl. This could be either a methyl, a methylene carbon, or a carbon with 1 hydrogen. Let's look at molecules that only have one unique alkyl carbon. Well, that would again only be this molecule right here, because it has one unique alkyl region, which would be this methyl group and this methyl group, which based off of symmetry would give us the same peak. Every other carbon is either part of a aromatic region, which would show up around 120 to 140, and also a carbonyl carbon, which would not have any hydrogen attached, therefore it would not show up in the alkyl region. For alcohol, we have 1, 2, 3 alkyl carbons. For this amine molecule, we have 1, 2, 3 unique alkyl regions. And for our ether molecule, we have 1, 2 carbons that are just regular alkyl carbons, plus 3 more, which would be 5. And in our nitrile molecule, just based off of symmetry, we have 1, 2, 3 carbons that would show up around the alkyl region. We only have one unique environment showing up, which again points to this specific molecule on the left, because the methyl groups are the only group in this molecule that would show up as one unique hydrogen environment, and because of symmetry, these methyl groups would show up together. And one last bit of information. Again, you don't have to go this far, but one more thing that we can use to further confirm that we're talking about the molecule all the way on the left is to count up all the carbon peaks. We have 1, 2, 3, 4, 5, 6 peaks on our carbon spectra. Well, that means that our molecule likely only has, or it has at least 6 unique carbon environments, which, going by symmetry, we have 1, 2, 3, 4, 5, and then lastly 6. So this is a molecule that has 6 unique carbon regions. Our alcohol, as far as carbon regions goes, has 1, 2, 3. This amine molecule in the middle, just based off of symmetry, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It would have plenty of carbon environments. This ether has 1, 2, 3, 4, 5 unique carbon environments, so not enough to reach 6. And based off of symmetry, this nitrile molecule has 1, 2, 3, 4 unique carbon environments. So again, this spectra shows us that we have at least 6. There are only 2 molecules that have at least 6 carbon environments, and our amine group would not match just because it does not have a carbonyl in its anywhere in this molecule. So again, those 3 bits of information: the aldehyde, or I should say the ketone carbonyl peak, the single alkyl region, and the fact that there are 6 peaks, all point to the fact that we're talking about this molecule right here. Now, in a perfect world, if there are 6 unique carbon environments, then you'll see 6 peaks. But sometimes peaks can overlap, such as in the case of this molecule, where if we count up the unique carbon environments based off of symmetry, we have this methyl group as one, the carbonyl carbon as a second unique carbon environment, and then going from the ring, we have 3, 4, 5, and 6 unique carbon environments. But if we count up the number of peaks on our molecule, or on our spectra, we have 1, 2, 3, 4, and 5. We have 5 carbon environments, or 5 peaks, yet our molecule has 6 unique carbon environments. So what this probably means, and this will typically happen, especially in the aromatic region, you may see peaks overlapping, such as in the case of this particularly large peak in the aromatic region. What we do know for a fact is this peak has to be to this alkyl carbon, something that's pretty standard, either a methyl group in this case, and our carbon that is bonded to, that is participating in a carbonyl group, that specific carbon that is double bonded to oxygen, that carbon is represented by this peak all the way around 200 parts per million. Our aromatic region, well, that's just going to show up between 120 to 140. And even though there are officially 4 unique carbon environments, we only see 3 peaks, mainly because this one on the right is probably some overlap. It could be, say, these 3 carbons right here, that are furthest away from the carbon bonded to the carbonyl carbon, or perhaps 2 other environments on the benzene ring are just overlapping for whatever reason on our spectra. So sometimes you will have a situation where carbon environments overlap, but usually that's mainly just an aromatic thing, unless you have a lot of different alkyl groups going on, like plenty of different methyls and so on. Now, what we were looking at before was just a regular broadband decoupled carbon-13 spectra, which is essentially labeled C NMR. What we're going to cover in now is an overlapped spectra, where we have our regular carbon spectra on the bottom, which tells us every single unique carbon environment. And on top is going to be a spectra from a DEPT, or distortionless enhancement by polarization transfer spectra. Now, there are 3 types of DEPT carbon NMR. There's DEPT 45, DEPT 90, and DEPT 135. Essentially, all types of DEPT spectra, they tell you which carbon peaks on our regular carbon spectra are carbon environments where the carbon is bonded to at least 1 hydrogen. So if we notice some of the peaks from our regular carbon spectra overlap with some of the peaks on our DEPT spectra, that's because it's representing the same carbon environment. Now for DEPT 45 and DEPT 90, which are not part of this worksheet, but you might see if you go on to a later chemistry course like analytical chemistry, DEPT 45 will have a peak for every single carbon environment that has at least 1 proton. depth 90 will only have peaks for carbon environments that have only one proton. For what we're going to deal with in this worksheet, we're dealing with depth 135, which, as you can see, has some peaks that show up above the horizontal axis for the depth spectra, or are positive peaks. And in this case, we have a peak that shows up below the horizontal spectra, the horizontal axis, or it can also be called as having a negative peak. Well, here's what happens. For any of our carbon environments where the carbon has 1 or 3 protons attached, they're going to show up as positive peaks, or upward facing peaks in our depth 135 spectra. For any carbon environment where the carbon is bonded to only 2 hydrogen atoms, they will show up as a negative peak or a downward facing peak on the depth 135 spectra. And for any carbon that is not bonded to any hydrogen, well, those quaternary carbons will just not show up at all on the depth spectra. For example, this peak all the way on the left at around 175 parts per million, that is in the carbonyl region. If that carbonyl is for an aldehyde, we would also see a corresponding peak on the depth 135. But we do not see any peak whatsoever. So this tells us we're looking at a carbonyl that's participating in a ketone group, or an ester group, which is what we have in our molecule right here. That carbon is a carbonyl that is not bonded to any hydrogen. So it will be its own unique carbon environment that shows up on the regular carbon spectra, but because there's no proton or hydrogen attached to that carbon, it will not show up on the depth spectra. Now, another thing to look at is this peak right here, which is labeled number 3. It also does not show up on our depth spectra, which means that that is a carbon that does not have any hydrogen attached. On our regular carbon spectra, it is in the aromatic region. So that's how we know we're talking about this specific carbon labeled number 3. Because that is a carbon that is not bonded to any hydrogen, but it is part of the aromatic region. Another bit of information we can use is just that this peak right here on our regular carbon environment, this peak on our bottom carbon spectra shows up as a negative peak or a downward facing peak on our depth 135 spectra. So that would be an environment where the carbon or carbons are bonded to 2 hydrogen, not 1, not 3, 2 hydrogen only. And if we look at our molecule, we only have 1 carbon that has 2 hydrogen on it, and that would be the one to the right of the single of the oxygen in our ether group. So that's why that was labeled 1'. And just based off of numbering, 1', 2', that just means we're going in a different direction than our initial numbering system of just 1, 2, 3, 4, 5, 6, 7. Now, all the other carbons on our spectra, for our depth 135 spectra, we're looking at positive peaks, which means they're either carbons that have 1 proton or 1 hydrogen or 3 hydrogens attached to that carbon. Here, we're looking at an alkyl carbon that shows up in the alkyl region on our regular carbon NMR, but has a positive peak on our depth spectra. So likely that is probably going to be a methyl group, which we only see right there on our molecule. These peaks right here, well, let's look at these three. Those three peaks right there, they show up in the aromatic region on our broadband decoupled C NMR. On the depth 135, they show up as positive peaks. Therefore, they would be aromatic carbons that have only one hydrogen attached, which would essentially be the ones that are labeled 4, 5, and 6. Where again, 3 is an aromatic carbon, but it has no hydrogen attached, which is why it does not show up on our depth 135 spectra. Two more peaks to consider are essentially this peak right here, labeled number 7 on our broadband decoupled C13 spectra. Well, what we're looking at here and in number 2, we're again looking at carbons that are only bonded to either 1 or 3 hydrogens. We have 2 peaks, therefore there are likely 2 unique carbon environments. They're in the aromatic, or in this case, in the alkene carbon-carbon double bond region. Peak 2 and peak 7, they just correspond to these 2 carbons right here. Because if we look at each of those carbons, they would be in the alkene region of our C13 spectra, and if we count up the number of hydrogen attached to those carbons, we see that there would only be 1 hydrogen attached to carbon number 2 and 1 hydrogen attached to carbon number 7. And for our depth spectra, that matches because positive peaks are for carbons that are bonded to 1 or 3 hydrogens. Therefore, this is just further confirmation that these 2 peaks right here are for these 2 specific carbons because they're alkene carbons that only have 1 hydrogen. Therefore, they would show up on the positive end of our depth 135 spectra. So, depth spectra, it's just meant to help you determine if there's a peak on the depth spectra, those are carbons that have protons or that have hydrogen attached to them. And if on the depth spectra the peaks are positive, those carbon environments have 1 or 3 hydrogen. If the peak on the depth spectra shows up negative, then that carbon environment has only 2 hydrogen. And if it doesn't show up at all, those carbons do not have any hydrogen. Now, one more peak that I'm going to mention. Similar to proton NMR, the molecule of interest needs to be dissolved so that it can be analyzed. And deuterated solvents are used because that deuteron will not interfere with a hydrogen 1 or HNMR spectra. Now, since a carbon environment will always show up on a carbon spectra, the solvent that was used in this case was deuterated chloroform, carbon that is bonded to 3 chlorine atoms and also bonded to a deuteron, which is an isotope of hydrogen that instead of having a proton as its nucleus, it has a proton and a neutron as its nucleus. So essentially, this is a carbon that's not bonded to any hydrogen 1 isotopes. It's bonded to a hydrogen 2, which is why it will not show up on our DEPT spectra, but it only shows up on our carbon spectra. Just know that if it's labeled solvent, it's a peak that you're allowed to ignore because it's not actually from any of the carbon environments on our molecule of interest. Now then, your lab activity is essentially looking at these 3 spectra, or combination of spectra, and determining which of these 8 molecules those spectra are representing. And I will just say that for problem number 2, this peak at 0 parts per million, that is a peak that you can ignore. That is actually from a TMS peak, which is a molecule used as a standard to help calibrate or help align every other peak in our spectra. It's used in proton NMR as well as carbon NMR. So for number 2, if you're counting up all the unique carbon environments, just ignore this one at 0 parts per million. It's actually not from your molecule of interest down here. Just to explain what you're doing, for problem number 1, you have a carbon spectra and you have a DEPT carbon spectra. We basically have one peak right here that shows up negative on the DEPT spectra, so that would be a carbon with 2 hydrogen. Not counting this peak right here at 0 parts per million for question number 2, we have 1, 2, 3, 4, 5, 6, 7. So you would look for a molecule that has at least 7 unique carbon environments, paying close attention to the peaks that are showing up further downwind at a higher parts per million. And where problem number 2 only has the broadband decoupled regular carbon-13 spectra, no DEPT spectra. And then problem number 3 has the broadband decoupled spectra again, and then the DEPT spectra, where we see we have one peak, one carbon environment that shows up on our C NMR, but does not show up at all on our DEPT spectra. Therefore, there's no hydrogen to that carbon environment. So, your only task for this lab activity is just determine what is molecule number 1, what is molecule number 2, and what is molecule number 3. And to the best that you're able, please do attempt to label each of these peaks that shows up on your carbon-13 broadband decoupled NMR to carbons in the molecule that you believe is represented by each spectra. For example, if you chose, say, this molecule for one of your spectra, try to label one of the peaks as this methyl group. Maybe label it as A, this carbon as somewhere on the spectra, maybe label it B, this carbon could be C, and then you're allowed to label certain carbons based off of symmetry with the same letter. But basically, decide what molecule is from spectra or is from problem 1, what molecule is from problem 2, and what molecule is from problem 3, and then try to draw the structure of that molecule you choose, and try to label each carbon, and then label the peaks on the regular carbon-13 spectra to those peaks. And well, that will conclude this introductory lesson into Carbon 13 NMR. Peace out, everyone.